Assalamualaikum everyone. So today we're going to continue with question number 5, part C. It is asking for the reagent for step 3. Basically, this is something that you have not learned, but you will in the next topic. Basically, this is what we call a reduction. Okay, where you change your amide into an amine. Okay, so it's a reduction. Reduction, we usually use the symbol square bracket H. So the reagent for this is lithium aluminium hydrate. Okay, so that's part C. Next, we're going to look at the second part of this question, where it is talking about a angelic acid, which is C5H8O2. So the name acid should already give you a hint that it has a COOH, as you can see from the formula, that it has 2 oxygen, and then there is 5 carbon, 1, 2, 3, 4, 5. Now this 5 carbon may not necessarily be a straight chain, it may be branched, it may be branched or a straight chain. I do not know that yet. Okay. Another thing that I want to point out is the number of hydrogen. There are 8 hydrogen only in this molecule. Now if we just count first, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This formula suggests that there will be 10 hydrogen. Okay, so but the formula only has 8 hydrogen. That means there must be a double bond somewhere. Again, the position of the double bond, I do not know it yet, so I'm just going to put it there. Okay, this is not the correct structure yet, but if we count the number of hydrogen, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it agrees with the formula C5H8O2. That means in this angelic acid there is a carboxylic acid and an alkene. Okay, angelic acid reacts with H2 plus nickel to form T. Okay, so hydrogenation is obviously you know that hydrogenation means you are adding hydrogen onto the double bond. Okay, so it is correct that angelic acid contains double bond because it can be hydrogenated, right? To form T. So at the moment we don't know what T is yet, because even angelic acid we don't know what how it looks like, and I cannot just assume that the double bond is between carbon number 4 and 5. Okay, it can be here, it can be here. I don't know that. And also this carbon, it may not necessarily be in a straight line. It can be branched like that, or it can be branched here. So we'll have to use the hints given in the questions again. Okay, T undergoes the above synthetic route to form the amine U. So again, T will undergo this process to form a U, which contains nitrogen. Okay, so it says this route above. If you look at the route above, that means you're starting with a COOH and then you end up with an NH2. Okay, again, we don't know T, we don't know angelic acid, so I cannot draw what U is. However, the last hint here, the last point that is given in the question, U can also be made by reacting 1-bromo-2-methylbutane with ammonia, butane with ammonia. So this is a completely different reaction. So I'll use a different color, purple. So to form U, it is when, okay, so I'll write it down here, methylbutane. So butane is 4, 1 bromo, I'll put my bromine here, number one, 2-methyl CH3. Okay, maybe I'll draw it like this. Okay, easy to see. So then the rest of the molecule is just hydrogen. Okay, so 1-bromo 2-methylbutane will react with ammonia to give U. Okay, so this is an SN, well, it can be SN, no, it is an SN2 reaction. Okay, so based on your AS reaction, ammonia acts as a nucleophile. It attacks the slightly positive carbon, the carbon-bromine bond breaks, and your product will be an amine. Okay, so this is what U is based on the last hint. Okay, now I am confident, based from the last hint, that U has this structure. Okay, so I'm going to drag this, since I've already drawn this. I'm going to drag my drawing because I know it's confirmed that this is U. Okay, then you can work from U, which is already confirmed. From U, you can work back what T is, and then you work back what angelic acid is. Okay, both angelic acid and T exist as stereoisomers. Now, what is stereoisomers? Stereoisomers is cis-trans and mirror. Okay, so in the angelic acid, again, this structure is not the correct structure yet, right? You'll have to figure out where the double bond is. Okay, so I can tell you that the stereoisomer in angelic acid must be a cis-trans. Okay, so you have to think, you have to choose a position for the double bond so that this molecule, angelic acid, can have a cis-trans. Okay, so that means this position is not correct yet. Okay, and also based on this methyl group here, CCH3, this suggests that there is a hanging methyl group here. Okay, so you have to change your structure. So once you start, again, move the double bond. The double bond is not correct yet, but the methyl group is correct already, because if you look here, CCH3, same. Okay, next is T. Okay, so when angelic acid undergoes hydrogenation, what happens is the double bond is lost. Okay, the double bond now becomes a single bond with a carbon-hydrogen bond. So in T, you would expect there is no more double bond. Okay, I mean double bond CC. COOH will still stay. Okay, so what happens is that if there is no double bond in T, the only stereoisomers you can have is the mirror or optical. Okay, so that's my hint for you. Your angelic acid, the only confirmed structure at the moment is structure U. Structure of angelic acid is not correct yet, because you have to find the position of the double bond that gives the angelic acid the cis-trans molecule. Okay, and then once you are happy that the angelic acid has a cis-trans molecule, then you hydrogenate the double bond to get a T. Okay, make sure that your structure T has a mirror or optical isomer. Now, what's the criteria of a mirror isomer? You need a chiral center. Okay, a carbon that is attached to 4 different groups or 4 different atoms. Right, so I'll leave you to that. State the type of isomerism shown by angelic acid A and T. So that's basically, I've already given you the answer: cis-trans and mirror or optical. Okay. Next is question 6. Okay, for question 6, let's have a look at this. We start with step 1. You have a bromobenzene, okay, and then in step 1 you have attached your CH3 group. Okay, ayo. Okay, so CH3 has been added. So you have to look at your benzene topic. How do you attach an alkyl group to a benzene? Okay, so that's a hint, alkylation. Step 2 is not easy yet. Well, it doesn't say much. Step 2 is a blank, and then you add PCl5 is again a blank to form this final product. Okay, now if you notice that in the product V, in the final product, the bromine is the same, the benzene is the same, so the only thing that's different is this part. Okay, and it tells you to go from S to V, a CH3NH2 is being added. Okay, so an amine is being added. So you can see that amine is actually this. Okay, so attaching amine to a C double bond O. Right, so the hint there is another thing that you need to take into account is PCl5. Usually we use PCl5 to attach chlorine to something. Okay, so I'm guessing S will have this structure. Actually, I can erase this already. Okay, so S will have this structure, bromine with a benzene ring, Cl. Okay, acyl chloride. So acyl chloride then can be attacked by nucleophile. So the methylamine is a nucleophile. This methylamine is a nucleophile. The nitrogen with the lone pair attacks the slightly positive carbon, and then the C double bond O breaks, C double bond O reform, and the carbon chlorine bond breaks, leaving or eliminating the chlorine. Okay, so that's the first hint. That's probably the only difficult thing that you need in order to finish this step. Okay, so this is something for you to figure out. Okay, you go from CH3, there's an intermediate product. Okay, there's an intermediate product which is a bridge from a methyl bromobenzene to an acyl chloride. So you have to think about it. The hint is the acyl chloride comes from something. Okay, what is the starting material of an acyl chloride? That is the hint. Now moving on to step 3. Step 3 is easy because you are only you are attaching nitro, so that's the nitration of benzene. Step 3 is the nitration of benzene. Okay, and then this is probably the only thing that you wouldn't know, so I'm going to give you the answer. Step 4 is when we reduce the nitro group to a NH2 group. Okay, so step 4, you need tin plus concentrated HCl and heat.